All right, diving in today, we're going to be taking a look at agent-based modeling.
Okay.
And I know that name might sound a little jargony,
Right.
but stick with me on this because it's actually really interesting stuff.
Yeah, definitely.
Basically, we're talking about using AI to simulate how huge groups of people,
Mm-hmm.
like millions of people, make decisions.
It's really wild when you think about it. Like, we can actually create these virtual cities now,
Yeah.
populate them with all these agents, and these agents represent real people making choices. And you can see how all their individual choices sort of bubble up and create these big, complex patterns.
Right.
It's almost like watching a city come to life.
Exactly. And the paper that we're looking at today,
Yeah.
it takes this to like a whole new level because they're using these large language models, the same tech behind ChatGPT to actually power these agents.
Yeah, that's a huge step.
Right.
Because it's bringing us closer to simulating how people make decisions in the real world.
Totally. And it's like giving these agents a little AI brain upgrade.
Yeah.
And the researchers took this and they put it to the test by simulating how people in New York City responded to the COVID-19 pandemic.
Wow, what a test case.
I mean, talk about a real world scenario.
Yeah, absolutely. And the framework they used to do this is called AgentTorch.
Okay.
And it can handle these massive simulations.
Okay.
And they fed these models so much data, and not just basic demographic stuff like age and location,
Right.
but also things like occupation and how long it had been since the pandemic began. They even factored in things like pandemic fatigue.
Really?
See, that's interesting to me because I remember how real that feeling of pandemic fatigue was.
Yeah.
You know, and so they're trying to capture that human element in this simulation.
Totally.
So what did they find? Did it actually work?
That's the million-dollar question.
Right.
And the short answer is yes, it did.
Okay.
By giving these large language models more information to work with the simulation became really accurate at predicting things like who was isolating, who was still going to work.
Wow.
And how all these decisions kind of changed over time.
So more data equals smarter AI.
Yeah.
Which equals a more realistic simulation.
Right.
Makes sense. But I'm wondering about this.
Yeah.
Running a separate large language model for every single person in a city like New York.
Yeah.
That's got to be a crazy amount of computing power, right? That's right.
Like, how do you even...
It's one of the biggest challenges with this kind of modeling. It takes so much computing power to run a large language model for every agent in a large-scale simulation.
Yeah.
It would just be impossible.
Right.
You'd need millions of AI programs running at the same time.
Wow.
It would bring even the most powerful computers to their knees.
So it's like a computational traffic jam with millions of AI agents all trying to make decisions at the same time.
Right, exactly.
So how did the researchers get around that?
Well, they had to get creative.
Yeah.
And they came up with this idea of LLM archetypes.
LLM archetypes.
Yeah. It's a pretty clever solution.
Okay.
Instead of having a separate LLM for every single person,
Right.
they grouped similar agents together.
Oh, okay. So instead of a million individual AI brains, you have, say, like a few thousand.
Exactly.
Each representing a certain kind of person.
Yeah. And those archetypes share the same LLM.
Interesting. So you're cutting down on the processing power.
Exactly.
But wouldn't that make the simulation less accurate?
You'd think so, right?
Yeah.
But surprisingly, it didn't.
Really?
Yeah, this approach with the archetypes, it actually worked incredibly well. It reduced the computational burden significantly, but it still maintained this impressive level of accuracy.
So they found a shortcut without sacrificing the detail.
Exactly. It's all about finding that balance.
That's really cool.
Yeah, it's a big deal for this kind of modeling.
So they figured out how to make it work computationally.
Right.
But how did they actually test if these different approaches were accurate?
So to test the accuracy, they focused on two main things.
Okay.
Disease spread and the labor market.
Which makes sense.
Yeah, because those were the two areas most affected by people's decisions during the pandemic.
Exactly.
And they wanted to see if the simulations could actually predict what happened in the real world.
So it's like a giant AI prediction experiment.
Basically.
And what were the results?
Well, they tested a few different setups to see which one performed the best.
Okay.
First, they tried using what we call heuristic agents.
Heuristic agents?
Yeah, these agents basically follow pre-programmed rules.
Okay, so simpler AI.
Got it. Then they tested the LLM-powered archetype model.
The one with the shared LLMs.
Exactly. Yeah. And then Just for comparison's sake, they even tried running a simulation with a unique LLM for every single agent.
Wow, so like the max processing power option?
Yeah, they wanted to see what would happen if they went all out.
I bet that took some serious computing power.
Oh, yeah, it was a computational beast.
So what were the results?
Well, the archetype model, the one with the shared LLMs,
Right.
it actually performed the best.
Really?
Yeah, it was the most accurate at predicting both the spread of the virus and the changes in unemployment.
So the balanced approach wins again.
It seems that way.
Not too simple, not too complex.
Right.
What of the other models?
The heuristic agents, they were okay.
Okay.
Their predictions weren't bad,
Okay.
but they just couldn't capture the same level of detail as the LLM-powered models.
Which makes sense.
Yeah. A global pandemic is pretty complex.
Say the least.
And then the model with a unique LLM for each agent, it was just too much.
Yeah, I figured as much.
It was incredibly resource intensive.
Like trying to run the latest video game on a 10-year-old phone.
Exactly. It just wasn't feasible.
So the takeaway here is that the LLM archetypes,
Yeah.
they really hit that sweet spot.
They did.
But I have to imagine that the really interesting part comes when you use these simulations to look beyond what actually happened.
Absolutely.
And start exploring like alternative scenarios.
Exactly.
It's like asking what if on a massive scale.
Precisely. And that's where the real power of these models lies.
Okay, so we can create these really detailed simulations of real-world events.
Right.
But what I'm really interested in is using them to explore those what-ifs.
Yeah, that's where it gets really exciting.
Like having a time machine for data.
I like that.
So like what kind of what-if questions can we actually answer with this?
Well, let's go back to pandemic fatigue for a second.
Okay.
Remember how we were saying that the researchers factor that into the model?
Right.
Well, they used AgentTorch to simulate what would happen if the Delta variant had emerged a year later.
Oh, wow. So like a year later in the pandemic.
Exactly.
When people were even more burnt out.
Exactly.
Oh, that's kind of a scary thought.
Yeah, and the simulation showed something pretty striking, actually.
What's that?
It showed that if the Delta variant had emerged later when pandemic fatigue was higher, the outcome would have been very different.
And not in a good way, I'm guessing.
You're right. The model showed that people would have been less likely to isolate or change their behavior.
Because they were just burnt out.
Exactly. They were tired of restrictions. They were tired of being careful. And so the virus would spread much more easily,
leading to
a much bigger surge in infections.
Wow. It's crazy to think that just shifting the timing of that variant could have had such a big impact.
It really is. And it just shows how important it is to understand human behavior when you're trying to predict the course of a pandemic.
Right. You can't just look at the virus in isolation. You have to look at the whole system.
Exactly. It's about the interplay of biology and behavior and policy.
It really makes you realize how interconnected everything is.
Yeah, it's pretty amazing.
So we can simulate different pandemic timelines.
Right.
What else can we do with this?
Well, they also looked at the impact of different policy interventions.
Oh, interesting.
For instance, remember all the debate around delaying the second dose of the COVID vaccine?
Absolutely.
Well, they could actually use AgentTorch to test those different vaccination strategies.
I get it.
And see how they would play out in the simulation.
That's incredible. So instead of just debating hypotheticals,
right,
policymakers could actually see the potential impact of their decisions.
Exactly. And they could factor in things like vaccine hesitancy and people's willingness to get a second dose.
That's amazing. It's like having a crystal ball.
It's pretty close.
But instead of vague predictions, you're getting these data-driven insights.
And that's really powerful.
It is. It's exciting and a little bit humbling at the same time. Just realizing how much these models can reveal about our own behavior.
I know what you mean. It's like holding up a mirror to society in a way.
Right. And it makes you think, what else could we simulate?
Yeah, the possibilities are pretty mind-blowing.
What if we could simulate the impact of climate change or the effects of different economic policies?
Exactly. Or even something like the spread of misinformation online.
It's incredible to think about.
It really is.
And on that note, I think we'll wrap up this deep dive into the world of AgentTorch and the power of AI simulation.
Yeah, thanks for having me. It's been fun.
This is really groundbreaking stuff, and I can't wait to see where it goes from here.
Bye.
Thanks for listening.